Physical change. When there's a physical change to something, what are you doing to the atoms or molecules when you go through a physical change? You're just moving them around. One person said just pushing them around. You know, we're changing them in some way. We're changing the way it may look to us, but we're not changing the atoms or the molecules that are present. In other words, if we were to be in an initial state, in state A, and it's just a physical change, or let's say we've got at least two things together. We've got element or molecule A and element or molecule B, and we make a physical change. If it's actually a physical process, if I'm just going to write physical here just so we can differentiate between the physical and the chemical. If I've got molecules or atoms A and B together, and then I make a physical change, what will I have on the product side? Yeah, we could show it that way. It would be A plus B. We could just kind of show that it's only a physical change by maybe going B plus A, you know? That's fine. But if I've got salt and sand and I mix it up, what do I have? I've got sand and salt. I've got the same things I started with. So I might change its appearance, or I may make it, in the case of dissolving something, I may make it appear to disappear, but it hasn't really disappeared. All that's happened is that the molecules of whatever the solvent is, and that's the liquid part there that dissolves the thing, has accepted the solute, that thing that's being dissolved, and so the molecules of the solvent are all around it and appears to disappear because we're looking at them one at a time and they're too small for us to see. It's only when we bring them together to form clusters that we have enough of them that we can actually see them. So separating them out from each other is a physical move because chemically I have A and B when I start, and when I'm done I still have A and B, rearranged a little bit, looking like B and A. I haven't changed the atoms or the molecules at all through the process. However, in a chemical change, if I have A and B, and I draw this arrow, and this is how we typically use this arrow in a chemical equation, something is chemically happening. So I'm not going to mark it chemical. We just recognize this is chemical. This is different. This is just a physical mix. But A and B, what might I have as a product over here? I start with A, and I add B to it, and something happens, and at the end I have a new structure, molecule AB, compound AB, because I had A and I had B. Now, AB is not A, and AB is not B. AB is made up of some combination, some proportional mix of A's and B's together to form AB. But it's not the same structure. It's not the same atoms or molecules. It's the same atom count, but it's not in the same form. Some reaction has happened, and there's now actually a bond that's been formed through this chemical process that's holding A and B together. Okay? So chemically, in a chemical change, what you end up with is something different than what you started with. In a physical change, what you have at the end is the same thing you started with. Just may look different. That's why we talk about physical changes like ripping the paper. It's like mixing something in the solute. But you're not reacting it. This one, when I'm at the end, I can't simply, remember the physical changes, just you need to find some way to separate these two things using filters or, some physical way you can separate these things out. How are you going to separate A and B back to A and B? You can only do it with a reversing reaction. You've got to do some kind of chemical reaction to it to get it back to its original form. If you don't react it in some way, it's going to stay AB, and you can't separate them with purely physical means. Okay? That's the difference between the physical change and a chemical change. One is form, and one is actual compound. Actual structures have been changed through a chemical reaction. All right. So the second one kind of was answered in that explanation for the first one. What is the difference between reacting and dissolving? For example, baking soda dissolves in water, but baking soda reacts with vinegar. So if I had left those arrows up there, the first one would have been water and baking soda produces baking soda in water. But baking soda and vinegar produces, and it reacts and produces carbon dioxide and a few other things, right? But it produces something different than what you started with. So your left side reactants and your right side products would be different for baking soda and vinegar. Your water and baking soda would be the same on both sides of the mixing. Number 3, why are you warned about using aluminum foil in experiment 6.1? Now, some of you wrote down, because it makes a nasty gas. That's true, but that is just a symptom of what's really happening, right? Something has happened to produce the nasty gas. Why is a nasty gas produced? Because there's a reaction taking place. And so if you add aluminum foil, if you use aluminum foil, you've now added aluminum to the chemistry, and it throws the reaction we're trying to study completely off. Okay? So you can't add something that's going to also then react in the experiment. That's why they say don't use aluminum foil, because the aluminum will become part of the reaction. And part of that reaction is the production of a gas, and that gas is nasty. So for those of you that are, it's snowing, you don't do it because it's going to stink. For those of you that are chemists, they're going, hey, look at, it's winter precipitation. Oh, we don't use aluminum because it'll get engaged in the reaction. Number 4, one type of phase change we did not discuss, the book didn't, but we did, right, is sublimation. Sublimation occurs when a solid changes directly into a gas without passing through a liquid phase. Does sublimation occur when something is heated or when something is cooled? It's going from a solid. We would then normally see a liquid and then a gas. In the case of sublimation, it jumps the liquid phase. Does that happen when things are heated or cooled? If it's going to sublimate, it's going to happen when it's heated, because it's skipping the liquid phase and jumping straight to the gas phase. Remember, this direction is increasing energy, normally through increasing temperature or addition of heat. So this goes from solid to liquid, we call that melting, and from liquid to gas, we call that evaporating. Moving the other way, when we're taking energy out of the system, it's cooling. And so we're moving from gas to liquid, that's condensing, and going from a liquid to solid, it's freezing. And then the additional one is the skip over, which is sublimating. Okay, so sublimation happens when you go from a solid to a gas and it's being heated, it's being warmed. Energy is being added to the system. Number 5, if a liquid goes through a phase change and all you know is that the molecules slow down and move closer together, what phase did the liquid turn into? It slows down and they get closer. Now, the first one is true in all cases, right? When they slow down. The second one, the second stipulation, is they move closer together. That's not consistent for every substance we know, right? There is one exception, that when it cools and goes from a liquid and cools to the next phase, it actually gets farther apart, right? But for most everything, except for, and what is the one exception? Water. Water, when the molecules slow down and they eventually change phase into liquid, they actually get farther apart. Remember, that's why ice expands from the liquid, that the liquid takes up less volume than the solid, the ice. But every other situation, it's going to go from a gas to a liquid to a solid. Okay. And that happens as it goes from a higher energy to a middle energy to a lower energy. So where is the high energy on my phase indicators right here? Which phase has the highest amount of energy in the system? The gas phase, over here. Gases have so much energy that the molecules or atoms are moving so fast that they're pushing away from each other, they're bouncing off each other, they're expanding out. Then as you take energy away, they slow down more. They tend not to ricochet off each other, take up less space and less motion, until finally they move to the solid phase. So again, the hand motions that are becoming semi-standard around here, we've got the gas that becomes the liquid that then becomes the solid. Okay, so the question, if it goes through a phase change, if a liquid goes through a phase change and the molecules slow down and move closer together, It's now a solid. And is it or is it not water? It is not water. Because it's slower and, in this case, slower and closer, slower and denser. That's everything except water. Water would be slower and less dense because it expands from the liquid to the solid. Number 6. Here we go. We just answered that one too. What makes water an exception to the phase change rule? The fact that it has a greater volume as a solid than a liquid. So in terms of the standard, which is gas, liquid, solid, water is gas, liquid, solid. Hydrogen bonding. We'll get to it. The fact that the hydrogens and how they interact with one another throws the whole routine that everything else shares off. Okay? So it's why hydrogen bonding. Right now, that's all you need to know. Why hydrogen bonding? We'll explain it in more detail later. But remember the consequences of that. Because water has a greater volume than a liquid, that's why ponds freeze from the top down instead of the bottom up. That's why there's life that can survive over winter and not be frozen solid in the middle of the pond cube. Okay, because water freezes from the top down, and the ice on the top actually forms a thermal barrier to keep the water below it warmer than it would be if water didn't freeze on the top. Kind of seals it off and isolates it from the air temperature. Because air loses its energy much quicker than water does. So water becomes a heat sink that radiates heat, and when the ice forms, it holds the heat in. Yes, it's still going to be very cold. Yes, it's going to be like 3 degrees. Okay? But God's designed those creatures to be able to survive that temperature. It keeps them from being in the middle of a pondsicle, because in the middle of the pondsicle, everything just dies and gets frozen. Number 7. What's wrong with this statement? While substances like carbon dioxide, CO2, and dihydroxide, water, liquid water, while substances like CO2 and H2O can exist in 3 phases, it's impossible for metals to become gases. What's wrong with that statement? Metals can be gases. The fact that it's a metal doesn't mean that it's solid. It's a metal because of the way its characteristics. Remember, we talked about luster, we talked about how it's going to want to give away electrons. Those are the things that are characteristic of it, but ultimately, metals are giving up electrons. It's not simply based upon their form. We're used to seeing most metals as solids. But every element and every compound and every molecule, everything can exist at all 3 phases. Now, someone on your answer, you did write correctly, it's because of the temperatures. And I kind of repeated this several times. The reason why we know metal as being a solid is because at the temperatures and pressures that we're at now, these atoms and molecules are in a solid phase. And I can change their phase by changing the temperature and or the pressure. Now, we're used to thinking in terms of temperature, but it's actually a temperature and a pressure. Because remember, what's pressure? It really just signifies forces constraining things, keeping them close together. And remember, phases are based upon the ability for the atoms or molecules to be apart from one another. So usually what happens is as you increase pressure, you also increase temperature. If you think in terms of temperature, that's fine, but just remember it's a temperature-pressure combination. That everything can be a solid, liquid, or gas based upon a pressure-temperature combination. So you can, theoretically, move everything into solid, liquid, or gas. We talked about absolute zero a little bit and the hypothesizing about that. At absolute zero, all motion theoretically stops. When all motion stops, even the vibrations stop. What phase must everything be in? Everything's solid. There is no such thing as a liquid or a gas at absolute zero. Everything is solid. And then as you add energy to it, things at different points will convert and move into the different phases as you add energy to them, starting at absolute zero and moving up. Okay? So.
If something had, or like, if a vacuum had a metal in it, would the metal become gas? Or is it pressure makes.
It's a combination of low pressure and then adding energy to it. It's not simply one or the other. It's a combination of the two. That's why we can take, and we're not in a perfect vacuum in space. That's why a spaceship doesn't vaporize as it goes to the moon. It stays solid the whole way. And we're grateful for that, right? But it's a combination of pressures and temperatures. I just throw that in there because temperature, in terms of the way we normally think, temperature is the most significant thing, but actually pressure gets involved in that too. Number 8, lead has a density of 11.4 grams per milliliter. Okay, so we've got lead has a density of 11.4. Is it grams per milliliter? Whereas gold has a density of 19.3 grams per cubic centimeter. If we were to make two identical statues out of gold and the other out of lead, which would be heavier? Yes, ma'am? Gold? She's saying gold would be heavier. Okay. Anybody have another answer? Because every answer I've seen so far, don't mean to say, oh yeah, I want to take the minority decision. So far, everybody's answered it correctly that I've looked at. Now, what's one thing you have to remember? We've got 11.4 grams per milliliter and 19.3 grams per cubic centimeter. Are they the same units? They actually are if you know what, if you remember what. A cubic centimeter is a milliliter. So 19.3 grams per cubic centimeter equals 19.3 grams per milliliter. Now, for some of you, you may not have even read the units and just missed that whole thing altogether and just said, well, answered it based upon the number. I could have said 11.4 ounces per milliliter and 19.3 tons per milliliter. You know? So look at the units. Make sure you're talking about the same things. Which is more? Which has more if I change my units on you? 2 pounds of this or just 1 ton of that? See? They're completely different scale, different units. But in this case, 19.3 grams per cubic centimeter is the same as 19.3 grams per milliliter. So we've got identical statues that are made. Now, thinking through the word problem, if something is identical to something else, how do we know that the answer then is going to be gold? Which one is heavier? Because if they're identical in their shape, what else are they identical in? If they're identical in shape, then they're also identical in volume. Right. Identical shapes, they're going to have identical volumes. So whatever size it is, see, they don't even tell you in here how much volume the statue takes up. We just know that we have two statues that they both take up the identical volume. So with the identical volume, which one is going to be heavier? The one that has the greater density. Why? Because whatever the volume is, I get 19.3 grams per milliliter as opposed to 11.4 grams per milliliter. And we're talking about the same number of milliliters, the same volume. So the denser one would be the heavier one. Now you couldn't say that to make it more complicated. It might say a statue made out of lead that has 11.4 grams per milliliter and determined to have 1.3 liters of volume. And gold with a density of 19.3 grams per cubic centimeter with a volume of 0.87, something like that, 87 liters. Which one would be heavier? Well, now you've got to actually do some math, right? Now, if you know rho equals mass times volume, and you're given the volume of each thing, then you know that mass is equal to density times volume. And I could compute the mass of each statue using this formula. And when I'm done, I'll have the mass of each of them. Okay? And then the question is, which one is heavier? It's not saying how much does it weigh, because remember, mass is not the same as weight. Mass is the amount of stuff. Weight is a force. Weight is the force of local gravity acting upon that mass. But here's the deal. Whichever one has more mass is going to have the one with more mass is going to have more weight given the same gravity. So we would look at this and say, okay, in this situation, the gold one is more dense. The gold one has more matter per volume, so it has more matter overall, and the one with more matter weighs more. It's going to weigh more on Earth. It's going to weigh more on the moon. It's going to weigh more on Venus. It's going to weigh more on Mars. Now, if I took two of the same statue and I left one on Earth and took the other one to the moon, which one weighs more? Now you got to know the gravitational pull. And if you know the gravitational pull of the moon is 1/6 of that of the Earth, then you take the mass, you take the weight on Earth, then you compute it for the other object and take 1/6 of that, right? And now you say which one weighs more. Weight depends upon the local gravity. Mass is how much stuff is there. And by moving it from the Earth to the moon, I haven't added or taken away any stuff, but it weighs differently. That's why the astronauts going across the moon are doing those huge leaps, record-breaking Olympic kind of long jumps. No. It would be a combination of distance and velocity. You need escape velocity to get outside the gravitational pull. But at anything they could physically, personally generate, they're going to go up and come back down. They're not going to escape. They're not going to escape the pull of the moon simply by pushing off. You don't need a trampoline, one of those trampoline zones or whatever those things are, sky zones. You don't need it. You just go outside the ship and start jumping. And hope you don't rip your suit while you're jumping. That's bad. All right, number 9. Number 9 asks or says, okay. Number 9, a student measures the mass of an object as 2.32 grams. So 2.32 grams. And its volume is 34.56 milliliters. She then calculates the density to be 0.06712969. There are two things wrong with her value. What are they? What's wrong? First one. Too many numbers, right? It said her... What is that called? The significant figures. Right, it says she calculates the density to be 0.06712969. I'm just joining in the conversation. 0.06712969. Okay. So the first thing was the number of significant figures. Remember, the density is going to be the mass divided by the volume. In this case, it's going to be 2.32 grams divided by 34.56 milliliters. Now, I'm not going to worry about what the actual answer is here, but how many significant figures would the answer have? Okay? That's precision. Precision would say, and that's precision, it's when we're going to be adding or subtracting, right? Right now we're dividing. And we do division, it's by the number of significant figures. The number of significant figures, how many significant figures are in 2.32? Okay, so we've got 3 sig figs. And then on the denominator, 34.56. There's 4 significant figures. So what's the rule when you're dividing sig figs? The least number of significant figures. So the answer can only correctly have 3 significant figures, because 3 significant figures are in the numerator. It's the lowest number of significant figures. So my answer can only have 3 significant figures. So that's the first error. Now what's the second error? Say again, I'm sorry. No units. Right, there are no units. So this student took 2.32 divided by 34.56, and the answer is 0.06712969 footballs. Or pizzas. Or, I don't know. And really, the student's probably thinking grams per milliliter. For all I know, it could be grams per liter, or kilograms per cubic centimeter, or all different. Without a unit, it's really meaningless. Well, I would say it's not meaningless because, frankly, if I look at your exams and I see that you have the right, even if you had the long form, I know you're getting close. You've got the problem mostly right, but then you need to know, wait a minute, I can't claim that it's accurate all to these number of points. I can only take it to 3 significant figures. And what are my units? Because ultimately, a number without a unit is still insufficient. It could be true, but it's not correct. That's number 9. Any questions on number 9? All right, 10. What makes a chemical equation balanced? Go ahead.
If it has the same number of each element on the reactant and the product side.
Okay. The same number of elements, the element count. Now, this is where you need to be real careful with your vocabulary, what words you use, because several of you wrote down has the same amount. Amount doesn't tell me that you're counting the individual atoms. If you say I have the same amount of nitrogen, for example, on the left side as the number of nitrogen on the right side, that's true if I know that we're talking about counting them up. But if we're talking about the volume, the same amount would be the same number of milliliters, and that's not necessarily true. Okay? I'm not saying I took off for that. I'm just saying you need to understand that when we're balancing the equation, what we're doing is we're counting up the number of each element. And the number of atoms of each element matches the reactant side and the product side. It's not completely clear what you mean when you say we have the same amount of nitrogen on one side as the other side, right? There's several things amount could be, but if you say the same number of atoms of nitrogen on the reactant side and on the product side, now I know exactly what you're talking about and you're right. If you were to say the same number of molecules of this and this, no, it's not right, because remember, the chemical reaction might very well break molecular bonds and reform molecular bonds. It's the number of each atom on the reactant side has to match the number of that same elemental atom on the product side. Any questions on that? That horse, I think, is quite dead by now. So don't just settle for amount. Tell me what your amount is. It's the actual atom count of each atom. Has to match on the product and the reactant side. Number 11, what law requires that all chemical reactions have balanced equations? Note, this law was discussed in a previous module. It's the law of conservation of mass, or technically mass conservation, right? It's the law that says we have the same amount of mass on one side as we do on the other side. We can't create something out of nothing, and we can't destroy something and turn it into nothing. All we can do is rearrange it. The law of conservation of mass, or the law of mass conservation. And number 12, the last one, explain how a chemist could use the difference method in measuring the mass of a liquid. Now, a couple of you wrote down how to find the volume. It's asking the mass. Okay? So, how would you use the difference method in measuring the mass of a liquid? Yes, ma'am. Did you? Right. It's just the way we did it for the lab. Remember, I had 3 different people go up and you had the graduated cylinder, and you took the mass of the graduated cylinder, and then you added a liquid to it, and then you took the mass of the graduated cylinder and the liquid. The difference method would say, take the mass of the graduated cylinder with the liquid in it, and then subtract the mass of the graduated cylinder empty, and the difference is going to be the mass of the liquid. So the mass of the container plus the mass, let's say the liquid in this case, that's one measurement you made, minus the mass of the empty container equals the mass of the liquid. So the mass of your container subtracted from the mass of your container with the liquid in it, or the object in it, the difference there is going to be the mass of the liquid or the object, whatever it is. You wouldn't necessarily have to write that out, but that's the wording. You take the mass of the container and subtract it from the mass of the container with the object or fluid in it. And the difference is going to be the mass of the object or the fluid.